Welcome back everyone to another video in our Fundamentals of Structural Engineering course. In this video, we are going to learn about structure design of RC columns under normal and moment. In our last video, we learned how to design a column under a normal force. But when we say that this column is under only a normal force, we are making an assumption here that all vertical forces are perfectly aligned to the center of the column beneath them. If you look here, if this force coming from the column above is not exactly in the center of the column, let's say we have like 2 inches eccentricity between the center of the column and between the center of the column from above, this means that this column is actually going to have this normal force in addition to a moment that equals this load multiplied by the eccentricity. So in this case, this column is going to be under normal and moment also, not only a normal force. This doesn't happen only in case of eccentricity, but it also could happen due to lateral loads like earthquake or like winds. It is going to create also a moment on our column. In general, most of our columns are under the effect of moment, not only normal forces. So in this case, when we have two components from normal force and moment, we go to what we call interaction diagram. This is a simplified sketch for how the interaction diagram looks like. Here you can see that we have a component for the moment, and here we have a component of the normal force. And here, this is the edge of our column. Any point under this curve or inside this graph here, it is safe. If it is in this part, this means that the normal force is high, so this column is governed by compression failure. As it goes lower, this means that the normal force is lower and the moment is higher. This means it is controlled by tension failure. And if our point is outside this graph, this means that the column is unsafe. This is how the interaction diagram looks like, what I have been just describing to you. Here, these are the main data of this interaction diagram. There is a different interaction diagram for each FC prime value and F yield, but and also for each gamma, which is the percentage between this the D or the dimension between the reinforcement of both sides of the column and the total width of the column. So this is the width minus the cover from each side, and this is the total width of the column. This here, for example, this interaction diagram is for gamma equals 0.8, F yield 60 KSI, and FC prime 4 KSI. In order to use this interaction diagram, we need to calculate the horizontal component of this graph and also the vertical component. Horizontal component, or what we call Rn, equals Pn multiplied by E, which is the nominal moment. Pn is the normal force and E is the eccentricity, or this also means the moment, over Fc prime multiplied by Ag multiplied by H. Or here, if you have the ultimate moment, then it is going to be divided by phi multiplied by Fc prime Ag H. Using this equation, you can calculate Rn, which is in the horizontal axis here. In the vertical axis, you are going to calculate Pn over Fc prime multiplied by Ag, or P ultimate over phi Fc prime Ag. So based on this value and based on this value and based on this value, you are going to use this curve. Whatever the point you are going to choose here, you have here these lateral curves. Each one, it has a percentage of reinforcement, starting from, as you can see, 1%, 2%, 3%. It keeps going up till 8%, which is the maximum reinforcement for a column. And wherever your point is going to be after you go from vertical and horizontal, this will be the reinforcement percentage required for your column. So let's have an example of this. So here we have this example. A reinforced concrete tight column is subject to design axial compression force of 875 kips and design bending moment about its strong axis of 740 feet kips. The column's cross section measures 30 inch multiplied by 18 inches and the distance from the edge of the column to center of the steel in each face is 3 inches. The concrete specified compressive strength is 4000 psi and the reinforcing steel is grade 60. The required area of longitudinal steel is most nearly. So we will start first by calculating gamma of this concrete section so we know which interaction diagram we will refer to. Gamma equals h minus 2d over h. All of these equations, of course, are mentioned in the reference book. I'm going to show you in the end the chapter for the structural engineering in the reference book, so you know what is exactly included in it. H here equals 30 minus 2 multiplied by 3, which is 6 over 30 equals 0.8. We choose the 30, not the 20, sorry, not the 18, because it said that the moment is about its strong axis. So this means we will refer to the graph where gamma equals 0.8. We will start by calculating Rn, which equals P ultimate multiplied by E, which is moment ultimate over phi Fc prime Ag H. We choose this equation because here it is saying that this is the design axial compression force. So this is the value you are going to use it. 740 for the moment here, which is 740 feet kips. We will multiply by 12 to get it in inches over phi 0.65 for columns multiplied by this is the area gross, which is 18 multiplied by 30, and Fc prime equals 4. Based on that, we get that Rn equals 0.21. After that, we will calculate Kn, which is P ultimate over phi Fc prime, area gross, which means 875. This is kips over 0.65 multiplied by 4 multiplied by 30 by 18, which equals 0.62. Now we will go to the interaction diagram and I'm going to show you how to get the percentage of the reinforcement. So this is here our reference book. We will scroll down to the civil engineering chapter. We will scroll down till we find the interaction diagram. Here it is. Let's zoom and confirm that this is valid for us. This is for gamma equals 0.8 and Fc prime 4 ksi if yield 60 ksi. So this is valid for our condition here. We have here Rn equals 0.21. This is 0.2, so we are just adjacent to here. Let's calculate how many lines we have. 1, 2, 3, 4, 5, and it is between 0.2 and 0.25, so each one equals 1 step. So we'll go just beside here. We'll keep going up. Here it is opposite to 0.6, but it is 0.62, and here in the top we have 1, 2, 3, 4, 5 also, but it is between 0.6 and 0.7, so each one equals 0.2 actually. So between 0.21 and 0.62, this is going to be our point here. So this point lies between this curve for the 0.03% and the 0.02%. Our point is here exactly. It is a little after the middle. You can measure precisely here this distance to find exactly which point. So we are a little after the point, the 2.5%, which is 0.025. So it is approximately 0.026. This is the percentage of the reinforcement. So we will go back here. From the diagram, we will get that rho equals 0.026. Now it is simple. We have the area, or not the area, we have the percentage of the reinforcement. So the area steered is going to be 0.026, which is the percentage of the reinforcement, multiplied by the area gross, which is 30, multiplied by 18, equals 14.04 inches square. So the answer is D, which is 14 inches square. So this is it for our video today. See you in our next video. Thank you.